Model validation is the process of assessing how well a model performs with data it hasn't seen during training, ensuring it's accurate and reliable for real-world use. In fields like healthcare or finance, inaccurate predictions can have significant consequences. Model validation helps reduce that risk. Now that our model has been trained and saved, I've created a simple Python script to load and validate our model. Let's take a look at the code. I've created a wrapper module to abstract away the TensorFlow, Keras, and graphing details so that we can focus solely on validation. If you recall, the last block of code in our Explore Data Python script split our taxi fare data into training and validation datasets. We trained our model using the training dataset. We will now use the validation dataset to assess the accuracy of our model's predictions with data that it has not been trained on. Our model is trying to predict fare, the label, by analyzing the relationship between fare and trip miles, the feature. First, we instantiate a model object from our wrapper module, passing in our validation data, our features, columns used to make predictions, and our label, the column containing the value we are trying to predict. The last line of code in our training script saved the trained model to the file system. Loading the trained model loads the configuration, weights, optimizer, and metrics from the file system. Next, we call our model object's predict method, which will use our validation data to make fare predictions. It will also calculate the root mean squared error for the model's validation data predictions. We then finish up by graphing the model. Now let's run our script and see how accurate our model's predictions are. We print our model's summary, which displays information on the layers, their types, shapes, and number of parameters. We also print the root mean squared error for our model's predictions, as well as the predictions themselves. Now let's look at our model plot and see what it tells us about our model's accuracy. Fare, the value that we're trying to predict, is on the y-axis, and trip miles, the value we are using to make predictions, is on the x-axis. The red line is our model's prediction line. The blue points are 200 samples of our validation data. Visually, our prediction line looks pretty good. If you look at the graph's heading, you will see the root mean squared error calculated from our validation data and our predictions. If you look back at the root mean squared error from our model training, it was 3.7192. The root mean squared error for the validation run is 3.8504, which is just slightly larger than our training run. Looks like our model's predictions are pretty accurate. But can we do better? When we were looking at the correlation matrix during the data analysis stage of our ML pipeline, we saw that not only was trip miles highly correlated to fare, but trip minutes was as well. Our scatter plot also showed a strong correlation for trip minutes. Let's try training our model using trip miles and trip minutes to see if it results in a more accurate model. Achieving this is pretty trivial. All we need to do is add trip minutes to the features array in our training and validation scripts, go through the training and validation steps again, and finally compare the root mean squared error of our model trained on one feature to the root mean squared error of our model trained on two features to see which is more accurate. We'll use the same hyperparameters that we did when training with one feature. Let's look at our plots and see what we can learn. You'll recall from your basic geometry class that the equation of a line is of the form ax plus by equals c. When we are training using a single feature, our model graph is a prediction line. The equation of a plane is of the form ax plus by plus cz equals d. When we are training with two features, the graph results in a prediction plane. From looking at the graphs, we can see that our loss curve has just the shape we want it to. The sample data from the model plot seems to line up nicely with our prediction plane, and the root mean squared error when training with two features is 3.4454, which is smaller than the 3.7192 root mean squared error we achieved when training with one feature. Now, let's save our model and move on to the validation step. Rerunning our validation script generates a model plot. We can see that the validation data is nicely aligned with our prediction plane. More importantly, the root mean squared error for our model trained on two features is 3.6074, which is lower than the root mean squared error of 3.8504 we achieved with our model trained on one feature. In this video, we walked through a simple validation script, ran it to make predictions and generate a graph, assessed our model's prediction accuracy, and improved the model's accuracy by training it on two features instead of one. I hope the contents of this repo have helped solidify your understanding of some basic ML constructs.